كمالة ال compensation في الجزء ده هنبتدي نتكلم على ال different compensators وأهمية كل compensator بيعمل ايه وبيأفكت السيستم ازاي. هناخد برضو example اللي هي نوعية من ال problems اللي هي بنقول عليها ال disturbance rejection problems. هنا في عندي على السيستم اللي واضح في السلايد ان في two signals داخلين، ال original signal اللي هي R of S و disturbance signal داخلة اللي هي مسميينها N of S أو noise whatever. يعني الاتنين داخلين على السيستم بتاعك. السيستم الأصلي اللي هو في الفيد فورورد في 1 على S في AS زائد B، في الفيدباك is unity زي ما واضح في السيستم ده. طيب احنا عايزين ايه؟ زي ما واضح من اسم السلايد يعني disturbance rejection، يعني انا عايز الاوتبوت ما يشوفش الديستربنس او النويز at steady state. هو ده المطلوب من disturbance rejection problems. طيب خد بالك احنا دايما بنعمل ايه؟ بنحط compensator على طول بعد الايرور سيجنال زي ما هو واضح في السهم في يعني في المكان اللي السهم اللي باللون الازرق ده في الفيجر موضحه، عشان نلغي تأثير الديستربنس بالنسبة للأوتبوت عند الستيدي ستيت. اوكي نتنقل عليه بعد. The first kind of compensator we shall use is the P compensator, proportional compensator. It will be put as shown in slide 17. It is required that C steady state equals 0 due to a disturbance or noise signal equals M over S, which is a step signal with magnitude M. The same procedure done in part 1 will be applied here. We will assume R of S equals 0. In this case, the output equals minus the error signal. The block diagram, when redrawn, will be as shown, and the transfer function will be a typical second order system. Calculating the steady state value of the output due to the disturbance, it will be equal to M over Kp. In this case, the disturbance, as said before, it's a step input with magnitude M. For C steady state to equal 0, Kp must tend to infinity, and of course infinity is not a design. However, what will happen if we increase Kp? From the characteristic equation, we can calculate omega n and zeta, as shown. When Kp increases, yes, C steady state will decrease, but zeta will also decrease. Refer to the maximum relative overshoot curve related to zeta. When zeta decreases, the maximum relative overshoot increases. And this is a drawback that we do not want. In this case, increasing Kp will make the C steady state due to the disturbance better, but for the steady state, but for the transient response, the maximum overshoot will be much higher, which is a drawback. This is what we mean by contradicting conditions. When we use a PI controller instead of a P controller, the transfer function between the output and the noise will be as shown. Note that the system has increased from a second order system to a third order system, and this is the effect of adding an integrator in the system. However, adding an integrator will cause the steady state error to be equal to 0. That is, we achieved the required. But you have to be very careful in this case about the order of the system since it increased. Note that also the type of the system will increase, and you have to be very careful regarding the stability of the system. In this case, for the system to be stable, BKP must be greater than AKP over T. This is a condition that you always have to maintain. The stability conditions must always be studied when you make a design. Now, a logical question is, what will happen if we just use an integrator without the proportional? The integrators cause the output at steady state to be equal to 0 due to n of s. So actually, it is the element that deleted the effect of the noise or disturbance. But be careful. In this case, I want you to make the analysis yourself, and you will discover the system will be unstable. Using the integrator alone, without the proportional element, will cause the system to be unstable. The second question is, what is the effect of a PD controller? What if we put a PD controller instead of a PI controller? Will it make a difference? This is a question for you to answer. We will now study the effect of PD controllers. This is another example. It's not a disturbance rejection example. It's just an input entering into the system. The original system in the feed-forward is 1 over AS squared, which are two integrators in series, and it's a unity feedback system. Note that putting a PD controller will result in the transfer function shown, and this system originally is a type 2 second order system. Putting the PD controller does not affect the type nor the order of the system. Therefore, the characteristic equation will be as shown in the last equation. Omega n and zeta can be easily calculated. The condition for the stability of this system is that all coefficients are positive, and the response of the system for a step input will be as shown. Note that this system, without the PD controller, will yield the characteristic equation AS squared plus 1 equals 0. This implies that zeta equals 0, and the system is originally an oscillatory system. Note that if a P controller only is used, the system will still have an oscillatory response. In conclusion, using a PD controller will improve the transient response and add damping to the system. Using a PI controller will improve the steady state output of the system or error of the system. Also note that in any design, you are required to design using the optimum design. It's not just a design. For example, if there are certain requirements that can be satisfied by using a PD controller, you do not have to put a PID controller. A PID controller will always satisfy all the requirements. But using a PD controller is better than using a PID controller, since you don't increase the type and you do not increase the system. Therefore, you decrease the complexity of the system due to your design. So when you are asked to design, if the question is design a suitable compensator without specifying which kind of compensator, you have to search for the best design, the optimal design, not just put a PID controller. I hope this lecture is now clear. If you have any comments, please send me an email and we may discuss your comments. Good luck.